This thin nickel, titanium wire has been trained into a hook. Cool it, bend it, and it can stay bent. Warm it again, and the hook returns. That looks like a metal remembering a shape. But the metal is not storing a picture. Its crystal structure is taking a reversible route, and we can follow that route one state at a time. The high-temperature phase is called austenite. In a nitinol actuator, that is the parent arrangement whose geometry was shape-set while the alloy was hot. Cool the wire through its martensitic transformation, and the atoms shift cooperatively into a lower symmetry arrangement called martensite. This is a diffusionless change. Neighboring planes move together rather than atoms wandering long distances and changing the alloy's composition. Martensite can form in several twin-related variants. Imagine two tiny shears that point in opposite directions. They make room for the new crystal locally, but they also accommodate one another, so the whole wire keeps almost the same visible shape. The crystal has changed, the ruler-level shape has not. That paired, self-accommodated state is twinned martensite. Now apply a load while the wire is cold. The easiest internal move is not to break the lattice apart. Twin boundaries travel. One variant grows while its partner shrinks. Material scientists call this debt-winning or variant reorientation. The wire takes a large-looking bend because many tiny shears now point in one preferred direction. Release the force while the wire is still cold and the bend remains. That is why this is not ordinary springback. The detwin martensite is stable at this temperature. Keep the wire through its austenite start and austenite finish interval, written A sub S and A sub F. The martensite reverses to the parent austenite lattice, and the programmed hook comes back. The memory is a crystallographic constraint, not a hidden miniature mold. Cooling and heating do not cross the same threshold. On cooling, martensite starts at M sub S and finishes at M sub F. On heating, austenite starts at A sub S and finishes at A sub F. The gap between those forward and reverse paths is thermal hysteresis. Its size depends on alloy, processing, stress, and microstructural friction, so there is no universal activation temperature for every memory wire. There is a second use of the same mechanism. Keep the alloy above A sub F, in a temperature range where stress can still create martensite. Pull the straight wire and stress-induced martensite appears. Remove the load, and it reverses to austenite without a heater. That is superelasticity, the same phase change, but driven around a stress loop instead of a heat and cool loop. An actuator is therefore a materials design problem. Composition and heat treatment set the transformation window. Geometry and a bias load turn the transformation strain into motion. Rate matters because the phase change absorbs or releases latent heat, and excessive stress or repeated cycling can leave plastic or fatigue damage. So the useful question is not, does this metal remember? It is, which phase, which variant arrangement, and which temperature or stress path make the recovery reliable?